Okay, everyone, welcome back. We are picking up on automatic differentiation, and today we will be done with automatic differentiation. We will look at a couple of intuitive patterns in Backprop. Then we'll look at the Jacobians in FC and ReLU layers in a neural network. These are the things that you've recently been implementing, which you'll see a sort of a clean formulation of everything. We were talking about differentiable programming, where we express computation as a DAG, and we are interested in algorithms or a family of algorithms for implementing chain rules on these computation graphs. The sort of two special cases that we've been working with are forward mode automatic differentiation and reverse mode automatic differentiation. We told you to start thinking about certain layers. Everything is a layer in a network, and the forward mode automatic differentiation operates in the same direction as forward propagation or computation of the loss. You're given as input the partial of the law of this input with respect to x, and you just have to compute the chain rule implementation at this layer. In reverse mode automatic differentiation, we're operating in the reverse order, but again, we're implementing chain rule locally at this node. We ran through an example of sin x plus x1, x2. We constructed the computational flow graph, and we showed you what forward mode automatic differentiation would look like on this computational flow graph. And we also showed you what reverse mode automatic differentiation would look like on this computational flow graph. And this is sort of what you'll need to do a lot of the homework as well. We're asking you to do some of this by hand. We gave you this nice little intuition that the last variable that a computational graph in the context of deep learning computes is a loss, and the first variable, let's say, is where first is loosely defined. It could be input data, or it could be the earliest parameter or anything. Think of these as variables with no parents in the directed acyclic graph, and these are variables with no children in the directed acyclic graph. And the loss with respect to x, forward mode automatic differentiation computes one column at a time of this Jacobian, and the reverse mode automatic differentiation computes one row at a time. And this is why in neural networks, there is typically only one loss. There are millions of parameters, and therefore we prefer backward propagation, because we compute all of the gradients that we're interested in, that entire row, all at once. We walked you through what are the differences. We walked you through the fact that forward mode, the reverse mode automatic might be faster if the number of output neurons is less than the number of input neurons. And we also talked about memory efficiency, that forward mode automatic differentiation is more memory efficient because you don't have to store the intermediate activations. You can just throw them away. We showed you a computational flow graph corresponding to a neural network. And we didn't get to this, but this is how you should think of it, that you should think of these as Lego blocks. And at these Lego blocks, if you can implement these sorts of operations, the loss with respect to input, loss with respect to parameters, if you can implement those operations, you can chain the entire process up, where you have a forward pass computing the loss in the mini batch, and a backward pass computing the gradients with respect to the mini batch, and then of course gradient descent to update the parameters, and that then completes the neural network training algorithm. So this is gradient descent implemented on neural networks. This part is backpropagation or backprop, computing the gradients. And of course, it needs the forward propagation because it needs to make calls to the activations. And these things can be put together in arbitrary configuration. We've been plenty clear about that. So that's where we're at. The plan for today is to do one more example and dive a bit deeper into backprop, because backprop, so far we've been sort of treating them as equal footing, forward mode automatic differentiation and backward mode automatic differentiation. But really backprop is all that you will predominantly deal with. So we'll do one more example, diving into building some intuition around backprop, and then we'll look at Jacobians in a couple of these layers that are of interest. Okay, so let's start doing that. So here's an example that we'd like to work with for backprop. This is another computational graph. This is a computation graph on 4 input variables. Here are input variables: X, Y, Z, and W. We see certain, they are set to these values: 3, -4, 2, -1. We see certain, the nodes, this is a product node, this is a max node, this is a summation node, this is a multiplication by 2 node. And so if we were to write down the function that this corresponds to, this would be f of x, y, z, w is equal to x times y, which is the product node, max of z comma w, which is the max, and there's connected by a sum, then there's a times 2, right? That's the function that is being implemented. This is f. And what we can do is we can introduce, just like we did, intermediate variables. So we will refer to this as w1, we will refer to this as w2. So this is w1, this is w2, and let's say this is w3, and the last thing is f. So this is our graph, and we'll do the same thing that we did, is that we will do we will try to implement both forward pass and backward pass in this computational flow graph. So the forward pass is pretty trivial. This is something that you probably will not stumble on or be confused by. You just set in the values of x and y. 3 and -4, you get -12 here. 2 and -1, the max operator returns 2 because 2 is larger. These two get added to get -10, and then you multiply this by 2 to get -20. Right? So this is your function f computation in the forward pass. What we'll do next is we'll run through backward pass, and we'll look at certain patterns in backward pass. So if this is f, right here we have to do f bar, which is the partial of f with respect to itself. That is 1. You've seen that now a couple of times, that backprop tends to start with 1. This was w1, w2, w3. We now have to compute w3 bar, which is the partial of f with respect to w3. F is just 2 times w3. That's the relationship. So this isn't hard, right? This is just 2. That's what we get back. So this is pretty. This one was pretty easy to get. So we get 2 on the backward pass. The interesting thing where we run into is at this plus sign, and so this is w1, w2. Actually, I'll have to skip slides anyway. Let's move. Oh, animation. Perfect. So here is my question. Let's try to compute what w1 bar and w2 bar look like. We know that w3 is equal to w1 plus w2. That's what we've written down. So when we have to compute w2 bar, this is just equal to the partial of f with respect to w2, which is partial of f with respect to w3 times partial of w3 with respect to w2. And everything that we've been doing in this class gives us this, we've looked at this again and again, that this first term is the input to backprop. This is w3 bar. This second term is the Jacobian of this layer. These are all scalars, so the Jacobian is also a scalar, but that's what we typically have to implement. For w3 equals w1 plus w2, somebody want to tell me what the Jacobian is? And I can pause a couple of seconds. What is the partial of w3 with respect to w2? It's a simple answer. 1. Yes, 1 is correct. Thank you. So W2 is equal to W2 bar is equal to W3 bar. And you can do the same analysis for W1 bar as well, that it's equal to W3 bar. Not an arrow, just a bar. Yes. And so this right here gives you an intuition of what's going on. We have gradients coming in, the W3 bar coming in, and we have W1 bar equal to it and W2 bar equal to it. This tells us that we can think of an add gate in a computation flow graph as a gradient distributor. That this is the gradient that came in, and it essentially distributed W1, and that same equals W3 bar, and W2 bar equals W3 bar, right? So on the forward pass, things got added. On the backward pass, whatever was coming in, it got distributed. Right? So an add gate is a distributor, is a gradient distributor. That's one way of thinking about it. It's good intuition to have, because it means that the more things that if you have a lot of additions in your computational flow graph, you should realize that those gradients will get sent a bunch of places on the way back. And this is important to understand. Okay, here's the next thing that we'll look at, which is this particular node. Now we're getting in W2 bar here, which is 2 because W3 bar was 2, and this is W1 bar, which is 2 because W3 bar was 2. We now know that W2 is equal to max of Z comma W, right? That's the function. By the way, you have already met a different max-like function in ReLU. You've met this object before, and we've plotted this object before. We've told you that the plot of this object is something like this, where you take a line which is y equals x, and you take another line which is y equals 0, and you're basically taking parts of it's the union of those two line segments, if you will, or rays, because they run out to infinity. And so if you think about W2 is equal to max of Z comma that, it's just a generalization of this, right? There are two input variables. And the way to think about gradients of these things, because we will be asked, for example, we'll be asked to compute Z bar, which is partial of f with respect to Z, times partial, which is equal to partial of f with respect to W2 and partial of W2 with respect to Z. So this first term here, that's pretty easy. That's just our input in the backward pass. We know that. We will be asked to compute partial of W2 with respect to Z. This is the Jacobian of max that we have to work with. And this is where things can get a little bit tricky, but you can make them easy by writing max as an if-else statement. So you can write max of Z comma W as Z if Z is greater than equal to W, and W otherwise else, right? Notice that the trickiness is in how we define the equality. Z greater than equal to W. I could have just as easily written Z strictly greater than W. That would also be a valid definition. And this, as far as computing W2 is not a problem. This becomes problem only in the gradient definition. But so far, what I've written down is correct. That we have Z greater than equal to W. If that's true, then W2 is equal to Z. That's just how max is defined. And if that's not true, then it's W. That's, again, how max is defined. It means Z is strictly less than W, so you pick W. And as soon as you do that, then computing this object, which is partial of W2 with respect to Z, becomes somewhat clearer. Well, this is a line. This is, W2 equals Z is just a straight line, and W2 equals W does not depend on Z. So I can just piecewise analyze that this is equal to +1 if Z is strictly greater than W. It is 0 if Z is strictly less than W, and it is not defined if Z is equal to W. Right? So I can just write down three cases. And this is, I'm doing this for z's and w's, but it's the same as if I had done this for this max of 0, x function. We know that the slope of this line on here is +1, the slope of this line is 0, and so it's just a matter of writing down the slopes as 0 depending on which side of the x-axis of the y-axis you're at. Okay, so far so good. We've written down the gradient of the layer Jacobian as an if-else function. Let me take a look at some questions. How is W3 a distributor if it is getting split into two but both equal to W3? So it's a distributor without a sum constraint, without a conservation of distribution constraint. Think of it as, like, maybe this is just semantics, that it's a splitter. I don't know. It's just a copier. You can use other terms if you'd like. All right. Okay, so now that we've computed this, and by the way, it should be clear that you can compute the partial of W2 with respect to X, with respect to W in a similar way, right? You just write these similar if-else functions. So now we know that, by the way, we know that Z is greater than W for the instance that we are interested in. So we are in this scenario, and so the gradient is the Jacobian is +1, and so +1 would get multiplied by W2. There is one more question. Why is it not defined if why is it not defined? There are a couple of questions. Why is it not defined? It's not defined because if you take the gradients, because this point right here is a non-differentiable point. Gradients require limits to hold from the right and the left, and those limits have to match, and those limits do not match. So if you just look back at what the definition of a gradient is, you'll notice that it's not defined at that point. Geometrically, the way to think about it is at that point, the slope of the line, and if the first derivative function, it has a discontinuity, it changes from 0 to 1, and at that point it is not defined because the right limit and the left limit are different. So it's okay to have a non-differentiable function as a layer? Absolutely, as long as you have a finite set of points of non-differentiability, it is perfectly fine. How is the equality condition handled in practice? In practice, there is no equality. That's too deep a line. Anyway, in practice, you never have to worry about the equality condition because there's up to numerical precision, those two values will typically never be equal in those cases. But yes, if they are equal, you're in trouble, and so we will end up adding noise to the inputs to get around that. But typically, this is not a situation that we have to worry about because it's only at a small finite set of points that this undefined happens. Okay, so that's how we're defining this. So what we've done is taken this 2, we've multiplied it by 1 so that it becomes Z bar is 1 here, and we've taken that and multiplied by 0 because that's how the if-else statements would work out. And so therefore we've computed this. And if you think about it, this max gate is acting as a gradient router because what it's doing is that, so I'll draw the max of 0, x plot again because that's just simpler. So the max of 0, x plot looks like this, and so the slope is either +1 or 0. And so that acts almost like a switch. Gradients on their way back either propagate or they do not propagate. Either you multiply by +1 or you multiply by 0. And so you can think of it as an on-off switch. Because we were doing max of Z, W, it's acting like not an on-off switch, but a Z versus W switch. When Z is greater than W, gradients flow back here. When if W were to be greater, the gradients would flow back to that branch, and the 0 would flow to the other one. So a max gate is a type of a gradient router. And that's important to remember because max gate will show up in the sense of a ReLU function. Can't we just use a subgradient for equality? Yes. So I was trying to not get into subgradients, but the analysis of subgradients requires convexity. So subgradient descent will not work if your function is not convex. You will not be able to prove that convergence. And yes, you can apply it to non-convex functions as well. Everything that we're dealing with has very few guarantees, but yes, you can. So in practice, what does subgradient mean? It means that if you have equality, just pick one of the line segments arbitrarily, and that's still fine. That's still a subgradient and a valid direction of descent. What if the noise causes equality? Finite precision, take two double or floating point numbers and add noise to them. The probability that they will cause equality is almost surely 1 minus 0, right? So that's the So now we know max gradient is a gradient router. Max gate is a gradient router. What about this multiplication gate? So we're getting W1 bar here, not there, here. W1 bar is 2. Let's see what we can do to compute the. So now what we have to compute is X bar and Y bar. X bar is partial of f with respect to x. It neatly decomposes the same thing that we've been doing is partial of f with respect to w1, partial of w1 with respect to x. This right here is x bar. This right here requires just a little bit of calculation to realize w1 is x times y. So partial of w1 with respect to x is simply y. So this object is x bar y, and if you compute, for example, y bar similarly, you'll get x bar times. So this, sorry, I messed up. This bunch of typos and errors. This is not x bar. This is not x bar. This is not x bar. I've been mindlessly copying a mistake. This is W1 bar, so you get W1 bar and you get W1 bar times X. Right. So X bar is W1 bar times Y. Y bar is W1 bar times X. And that tells us that whatever gradient is coming in, anytime we hit a product layer, we're going to send that gradient back, but we'll multiply it by whatever was the input from the other side. So X, what comes here is going to get multiplied by Y, and what comes here is going to get multiplied by X. So you can think of it as a gradient switcher of kind. So 2 times minus 4 became minus 8, and 2 times 3 became 6. So it's a gradient switcher if you of a particular kind, but it's a very weird kind of switch because it is multiplying by the input on the other side. Right? This input is getting multiplied here. So it's a somewhat weird operator, but I'll tell you in a second why it's important to think of it as a switcher and why this comes up in the context of neural networks. In practice, while training, do we only use gradients of weights, or do we also require gradients of inputs? Excellent question. For backprop, for training neural networks, most of the times, you only require gradients of weights, parameters. You do not require gradients of inputs. But if you think about it, if you think about how you construct neural networks, there'll be an X here, there'll be a W1 here, and there'll be a hidden layer 1, then there'll be a W2, and so on. So if you think about it, and then there'll be a loss. In order to get to the partial of loss with respect to W1, you will have to keep taking gradients. You'll have to get partial of L with respect to H1 as an intermediate variable anyway, and then you'll get here. The data layer is typically one extra hop after the whole thing. Typically, you never go all the way and compute this because you don't need it. However, for certain applications, and this will become clearer when we talk about visualizations in convolutional neural networks, you will compute gradients of loss with respect to input because you will ask the question, as I change my pixel, my RGB value, epsilon or a little bit, how much does the loss change or how much does my prediction change? And in order to do that, you will compute gradients of softmax outputs with respect to pixel values. But that's a rare case. In predominantly, we end up computing only the partial of loss with respect to parameters. Okay, so this is an aside. Don't worry about it. So gradient switchers. Why is this important though? This is particularly important. Let's see, do I have another slide? No. This is particularly important. I need to clean some of this up. The reason why this is important is if, for example, so y bar is equal to w1 bar times x. So what happens if this input 3 was 3000? What happens is that suddenly the gradients going back to the other side, the gradients going to y get multiplied by 10 to the 3, right? They went from 3 to 3000. So a factor of 1000 got introduced in the gradients of y. And this is important to remember because you will have layers in neural network where you will be computing, for example, HLI is equal to WI transpose X, right? Or you'll be doing something like that. It means that which is also an inner product and then a summation, right? It means if X is poorly conditioned, if I take all of my X values and I multiply them by 1000, the gradients with respect to W will get multiplied by 1000. And that is a problem. Suddenly when gradients are massive, the same step size will stop working. So on one data point, if data lives in 0 to 1, on another data point, it lives in 0 to 2000. On that first data point, you will get gradients that are smaller. On the second data point, you will get gradients that are an order of magnitude or 3 orders of magnitude larger because your data is poorly conditioned. Your data being conditioned is multiplying the gradient going to the parameters because there's an inner product somewhere. And inner product is doing a multiplication and a summation, and multiplication is a gradient switcher. Does that make sense? Does that intuition? Right now, I'd be looking at nods and hands, but we don't have that. So if that intuition doesn't make sense, feel free to ask me another question. Basically, you need to. The behavior in Backprop is why we spend so much time making sure, for example, that everything lives in the same magnitude, because otherwise gradients are getting multiplied by that magnitude. And you have to understand this in order to, Can't we normalize the data? Absolutely, you can. You have absolute control on X, so this is one reason why we invest in data normalization. But remember that in neural networks, after the first inner product or something, there are intermediate activations, and you might be performing dot product with intermediate activations as well. You have to make sure not only does X live in some normalized regime, you also have to make sure that these H's along the way, HL, also is somewhat normalized. And you do not have easy control of H. And in order to do that, this is what motivates, for example, batch norm or instance norm or group norm or any other kind of normalization layer, so that your activations also live in some manageable data regime. But good question. Okay, I think one thing that hopefully you've picked up is that there is a certain kind of duality that emerges in forward prop and backward prop. In forward prop, anytime there is a sum, anytime there is an X and a Y, and a W, which is X plus Y, when you get a W bar, that same W bar gets propagated on both sides. And this is something that we looked at in the previous slides. So summations become distributions on the backward pass, and distributions, so if there's X here, X here, X here, so if there's a copy operator, become, so if there's, for example, X bar coming in here, X bar coming in here, we will end up adding those two on the backward pass. This is just a direct consequence of chain rule and the sum of partial derivatives to get total derivatives. This is just a direct consequence of that. And this is something that you've seen in the past. We've shown you how in computational flow graphs, when you have gradients coming in from two different directions, you end up adding them. So there's a nice little duality forming that sum becomes distribute, and so sum becomes copy, copy becomes sum, and then that's nice to keep in mind. Sorry, just to confirm, we need to know that multiplier gate is a gradient switcher to know the importance of having our data to be in the same order of magnitude. Yes, that's why we were building up that intuition, so you could see why it was important to have data live in the same order of magnitude, to have data be normalized. And when things don't work, you should go and look at your gradient magnitudes and then go look at activation magnitudes to see what's happening, as to why, for example, if you're ever getting nans in your loss functions or some computation, why that's happening. There are numerical precision issues, there were magnitude issues, because if some things are really high magnitude, at some point you're going to exponentiate and normalize them, and so you have to be careful about what you're exponentiating, and so on. Okay, and in general, we're going to have modularized implementations of these things. So you will typically define a computational graph class, and for every every node or every computation object, you will define a forward pass and a backward pass, which gets applied in the topological ordering and the reverse topological ordering. And so for every gate or object, as long as we can make calls to forward and backward, we'll be able to chain them together in a for loop manner. We'll be able to just call all the forwards and call all the backwards. And so this is all that you have to implement for every layer if you were writing your own layers. In most of the times, you're not writing your own layers. You're using existing things that are already implemented in libraries. And so in order to implement any particular layer or any particular operation, you have to implement, for example, a forward function and a backward function. The forward function here, z, is just multiplying x times y and returning it. The backward has to take in this variable called dz, which is the z bar, the loss with respect to z. It has to output dx dy, which is the loss with respect to x and y. And this is typically what you have to implement in most cases if you're writing your own modularized implementations. And in this case, for example, z is x times y. You also need to store x and y, because in order to compute dx and dy, you will need that stored copy to multiply with dz and dy. And this right here is telling you, is another way of reminding you that this is the memory overhead of reverse mode automatic differentiation. That reverse mode automatic differentiation requires knowing what the inputs to any particular layer. This is just a layer. You do not know what came before it. You do not know what came after it. You don't even know when this layer is being called in the topological ordering. All you know is you have to be able to implement z equals x times y, but you also have to remember the inputs, because those inputs will be called again in order to computing dx and dy. And this is important to remember as a concrete demonstration of that fact. As a rule of thumb, all inputs to layers should be normalized. Well, in an ideal world, yes, but remember that inputs to layers, you cannot just inject yourself in the middle of a layer and simply normalize it, right? I mean, right now, so z is the output here, right? And z is the output to this layer. How are you going to normalize it? You need to know what all the other z's are if you're doing batch norm or so on in a particular batch. And then that's a particular operation that you are adding at the end of z, and that operation has to be differentiable and so on. So it's not trivial to make sure that everything lives in the same range and the same set of values. Can normalizing data distort, change the results, prediction, and relationships between x and y? Absolutely, it can. I mean, if for example, you have a data set of x1 and x2, and this is, for example, class 1, which is a cluster around 0, and this is, for example, class 2, which is a cluster around 0 as well, but has a different magnitude. Or imagine if I drew the first one as a circle and the second one as a ring. Imagine there were just two rings at two different radiuses, and you decided to normalize the magnitude. You would lose the very information that makes them separate. So yes, normalizing data can actually make it harder for you to predict why. The hope here is that we don't have to do zero mean unit standard deviation. There can be any other ways of normalization as well. And the hope is that your data is high dimensional enough that you're not losing all information by losing the magnitude. Here, it's a two-dimensional data, and so magnitude is really represented in that radius, and that's what you normalized over. And so you absolutely lost that. But in a higher dimension data set, maybe that's not, you don't lose everything by doing that. Yes, they're just out of order. Sorry, that's fine. Does duality hold for max and mult as well? No. This duality, this specific duality that I was talking about, this only holds for sum and copy. For max, we already told you it's a gradient switcher, and for multiplication, it's a slightly a different operation. But no, this particular clean version of the duality only holds for the sum and copy operations. And you can write down the math to see that it doesn't hold for anything else. Okay. And if you open up a library like Caffe, which it's been a few years, you probably won't do that now. Now you do go to PyTorch. Caffe, for example, had different C++ functions corresponding to different libraries. So there was a absolute value layer.cpp, there was an accuracy layer.cpp, there was an argmax layer.cpp, base conv layer, and so on. And so for every kind of layer, you have a function implementing both a forward and a backward pass, and you could implement your own. And now you just kind of pick and choose from these things. And for example, there was a Caffe sigmoid layer implementing in the forward pass the sigmoid operation, 1 over 1 plus e to the negative x, and in the backward pass implementing the gradient or the Jacobian of this with respect to x, 1 minus sigmoid times sigmoid, and it's just the chain rule implemented at this layer. Okay, let's get started with looking at the Jacobian of a rectified linear unit or a ReLU unit. This is something that we've looked at a few times. ReLUs are things that we've met. And so let's just look at a couple of things about ReLUs. So remember, this is HL minus 1. Let's say this is a 4096 dimensional vector. This is some layer L in our network. This is HL, which is also, let's say, 4096. We know that ReLU is expressed as HL is equal to max of 0, HL minus 1, where these are both vector quantities. Or if you want to express this as a scalar, you say the ith dimension, so the ith neuron here, HI is equal to max of 0, HL minus I. So you just kind of look at what the input is. So now the question that we'll be asking is the Jacobian of this layer. So let's say if this is the input HL minus 1, this is the output HL. During backprop, we will be provided the partial of the loss with respect to HL, and we will be asked to compute the partial of the loss with respect to HL minus 1. And the question that the key computation that we will need to address along the way is the Jacobian of this layer, right? HL minus 1. So this is a simple build-up. This part is not particularly hard. So the first question that we should address is what is the size of the Jacobian matrix? So partial of HL with respect to HL minus 1. Given the parameters that we have defined, what is the size of this matrix? Folks, please enter it in the chat. Not a particularly tricky question. Input is 4096, output is 4096. How large is this matrix? (4096 times 4096). Yep. That part's easy. Yep. 4096 times 4096. That's the dimensionality of this matrix. And in practice, it's important to remember that it's actually an even larger matrix. So if you had a batch of 100 examples, then you'd be computing a matrix of 4096 times 100 times 4096 times 100. So technically, it's even larger matrix. But let's ignore that for a second, and let's focus just on a single data point. So this is a 4096 by 4096 times matrix. The question we'd like to ask is so the question we'd like to ask is HL minus 1. The question we'd like to ask is there a structure to this matrix? For example, what do the diagonals versus non-diagonals of this matrix look like? Any thoughts? Does this matrix have any particular structure? Diagonal. Yep. We know that HIL is max of 0, HIL minus 1. This HI does not depend on any other J. So this matrix, the off diagonals have to be 0 because the partial of HLI with respect to the partial of HL minus 1J is 0 whenever I not equal to J. Right, so that part's pretty clear that the off diagonals are 0. What about the diagonals? Are the diagonals always 0? Are they always 1? What do the diagonals look like? Any guesses? What do the diagonals look like of this matrix? We've covered pieces of this several times. 1 or 0. Yep. It's binary 1 or 0. Yep. So the diagonals of this matrix are basically checking their indicator variables for whether HL minus 1I is greater than 0 or not. If the input coming in was positive, the diagonal is 1. If the input coming in was negative, the diagonal is 0. Right. So this part is pretty clear. The off diagonals are 0. The diagonals are basically switch-like operators. They're plus 1 or they're 0. And this being the Jacobian of this layer kind of tells you what it's actually doing in Backprop. It's basically it's basically letting the gradient pass through or not, depending on whether HL minus 1I was positive or negative. Okay, so that's what this looks like. That part's easy. Now let's look at the Jacobian of the FC layer, which is the fully connected layer. So again, we'll draw a similar box. We'll say this is layer L. We have HL minus 1 coming in, and let's say it's some R C1. It's producing HL, which is some R C2. During backprop, we get as input the partial of loss with respect to HL, which is a sort of 1 cross C2 vector, and we have to produce partial of loss with respect to HL minus 1, which is a 1 cross C1 vector. There is a W matrix, and therefore we have to produce this. We know that this fully connected layer HL is simply W times HL minus 1, right? And we're assuming that the bias has been incorporated into the column. If not, it would just require special treatment. But yeah. So there are two sort of things we have to calculate. And the other thing, the reason why we're doing this in class is there's a particular intuition corresponding to a calculation that you'll see. So there is this object you have to calculate, and there is this object you have to calculate, right? This is what you did in your assignment. And let's do those calculations one at a time. They're somewhat illustrative. The calculation that comes in handy is to remember two ways that HI is equal to that this matrix W is actually a matrix of weights W1 to WC2 weights on the rows, and HI is WI transpose HL minus 1. Right? So both these expressions are useful because they end up being useful in two different calculations. So let's calculate the first thing that we've been asked. Turns out that it's easier to calculate this in terms of each of the weights WI as opposed to the full matrix. It's far easier to calculate because things just end up becoming a lot simpler. And this is where I saw several people get tripped up in their calculations. And this part is pretty easy. If you just apply chain rule, you get the partial of loss with respect to HL and the partial of HL with respect to WI. As soon as you do this, this right here, the partial of loss with respect to HL, this is the input. We're in backprop. We already know this, and this is a row vector of 1 cross C2. And the other object is this matrix of that we have to compute, the partial of HL with respect to WI. And this is the same sort of structure. If you look at what is the structure in this matrix, turns out it's got 0 rows because changing WI does not affect any other output other than HI. So you will end up getting the partial of HI with respect to W. That's on the ith row. Everything else is 0. So everything that's not I is 0. And from this expression, it becomes pretty clear what should go on this row. What should go on this row is HL minus 1 transpose, because HI is equal to WI in a product. We've already done this many times. And so it becomes very, very clear that if there are 0 rows and there is one number here that will get pulled out, so what we'll get is partial of loss with respect to HLI times HL minus 1 transpose. So that's our gradient with respect to the parameter. The gradient with respect to the parameter WI is that you just take your incoming gradient with respect to HI and you multiply that by the feature or the incoming activation during the forward process, HL minus I transpose. And this is just a vectorized version of the scalar multiplicative operator. Z is equal to W times X. And so when you have to compute dx and dy, you just take the gradients flowing backwards and you multiply that by X or Y, depending on which one you're taking that risk. This is just a vectorized way of expressing that same thing. And so this is the Jacobian of the FC layer, one of the Jacobians. And the other one is actually slightly easier to implement. So the second direction that we need to compute is partial of loss with respect to HL minus 1. This one is somewhat easier. We know that HL is equal to W times HL minus 1. This is a matrix again, and therefore the partial of loss with respect, let me just erase that a second. Therefore, the Jacobian of HL with respect to HL minus 1 is just the W matrix. We've done this in class a couple of times. Therefore, this expression is equal to the partial of loss HL times HL with respect to HL minus 1. And so this is equal to the input that you're getting, input of gradients times W. So you left multiply. So again, this is something that you have already computed, that we have an input gradient and you left multiply it with the weight. The reason why I wanted to quickly cover this again is that if you think about it, there is a nice little duality happening between this expression and the backprop expression. So if you compare these, there is a duality happening here. In the forward pass or forward prop, you take the matrix W and you right multiply the input or the activations. During the backward pass, you take the matrix W and you left multiply the gradients that are flowing on the way back. Right multiplication and left multiplication have a nice geometric sort of intuition to them as well. We draw sort of right multiplication like this, right? I mean, we sort of often draw these things as circles. We say this is HL minus 1. This is 1 all the way till HL minus 1 C1. This is HL1 all the way till HL C2, and we say pick an ith neuron, and if you want to know what the activations to this are, this is HLI, and this is WI1, this is WIC1. So these are the WI values, and you input H activations, and we calculate the ith activations by summing together the linear combination of these things. This is right multiplication, and left multiplication has its intuition that you simply run this network in reverse. And by that, what I mean is this input is partial of loss with respect to HL1. This is partial of loss with respect to HL2, so on, till partial of loss with respect to HLC2. And if you think about a jth neuron here, if you connect these edges and have exactly the same weights, so the weights on these edges now, so the ith neuron, the output corresponds to a particular row of W, and the jth neuron on the input corresponds to a column of W. So the W matrix, if you think about a particular column of that, colors, so my figure stays consistent. The red corresponds to a particular row of W. This is WI transpose. And if I take a particular column of W, and let's say it's the jth column, each one of the weights on that column are corresponding to weights on the blue edges. And so when you left multiply the gradients, what you're doing is simply running the network in reverse. You are accumulating here the partial of loss with respect to HL minus 1J at this value. So it's this nice little dual operation, both from a geometric perspective, from a flow perspective, and also from a matrix multiplication perspective, right matrix versus left matrix.